We start the later section of this lecture. We went through all the details about this frequency domain performance matrix and its relationship to stability and step load response and step response. And the final thing I'd like to address is this phase margin. Phase margin is extremely important. Phase margin is margin of stability in terms of the additional phase it can introduce to the system while maintaining the stability of the system. So initially the phase margin is derived from the concept of the margin, but this is very important. So it can be used all the performance measure index for all the performance of this converter. Okay? So if you have good phase margin, 60-degree phase margin, everything is okay. Okay? If you have small phase margin, system converter becomes easily unstable, and even though converter is stable, the performance is very lousy. Okay? So this phase margin has the prime importance of this designing the feedback controller. So let me discuss the phase margin and converter performance in some details. Okay, this is the summary of we went through. So this is the loop gain, and the phase margin is very large. So when evaluating phase margin, you take a look at the 0 dB crossover frequency of the loop gain magnitude and difference magnitude at that frequency. And this minus 180 degree is phase margin. And the bandwidth, control bandwidth is up to this omega c. Okay? So this is very good. Okay? Phase margin is very large, and this bandwidth is very wide. So this is the best possible design, probably. And with this, we have this near optimal output impedance characteristics. And this is very nice audio susceptibility, and step load response and step input response are excellent. Okay? So just obtaining this will guarantee this. So phase margin is very important. And for the smaller phase margin, so phase margin is smaller than previous case. So we have this 35 phase margin, and the bandwidth is narrower than the previous case. Okay? So this is worse in bandwidth, in frequency, and it shows this peaking. Okay? So step load response becomes oscillatory. Of course, this decaying rate and everything can be predicted from here, and characteristics of this can be predicted from here or from here. Okay? So this is the linear time invariant system. It's not a linear time invariant system, but we modeled as a linear time invariant system. So we are using all our previous knowledge. So nothing is new when what I'm talking to you. That is all based on the classical control theory or circuit analysis theory. Okay? So we are just adapting that. We are borrowing that knowledge to here. Okay? For that, we are using the small signal model because we have not discussed the small signal model yet. We are using the result of the measurement or result of the computational simulation. Okay? Later on, starting from the next week, we'll be discussing the modeling of this PWM converter. Okay? Then we forget about these things sometime. Later on, for the control design, we combine them together to design the feedback compensation. Okay? All right. This one is okay, right? So this is bad, this is bad, and this is the bad, and everything is bad compared to the previous one. And the phase margin is further reduced. It becomes almost unstable. So phase margin is here. It's just marginal. Okay? 2 degree of phase margin, and very narrow bandwidth, and high peaking, and very oscillatory behavior. You cannot use this system, obviously. Okay, so I think we discussed more than enough. Okay, the previous story all applies here, right? Because this decaying wave and something, this oscillation frequency and this some first dominant pole, all of that, and this pole, single pole here. Okay, just use your ruler or just hand sketch. Do not take a look at the computer simulation using MathCAD, MATLAB. That will hurt you. Okay. Then your brain got boiled like egg. Okay. So use your insight and engineering sense and the knowledge you obtained here. Okay. And this and one very important topic. We discussed the stability using something else. Okay. We define the stability using this sinusoidal input injected in the feedback path, and we discussed the returned signal, and we analyze the phase minus 180 degree and the ratio between injected signal and the measured signal, and somehow with that you can establish some stability criterion. The result is this one. So this is the loop gain plot. Okay. So this is the line segment A. If this passes this line segment A, then it is stable. It passes this point, critical point, marginally stable. It passes outside of this, then becomes unstable. Okay. That is our result. Okay. But that result is same as the Nyquist analysis, formally applied. Okay. The formal Nyquist analysis, when that is simplified, that becomes the same as our previous discussion. So this is a good practice to introduce some of the Nyquist criterion. Okay, just the central idea only. Okay, so when we are talking about the Nyquist analysis, we are talking about this. There is some special equation, 1 plus TMS equals 0. We want to know root of this equation is in the right half plane side. Okay. If there is a one or more pole is right half plane side, then system is unstable. That comes from the definition of Bode stability in linear time invariant system combined with the conformal mapping theory, okay, complex analysis and conformal mapping theory and the Cauchy's theorem. Everything is combined all together, and using that result, the Nyquist established very simple criterion to judge this mathematical problem. This is a mathematical problem, not a stability problem. Suppose you have this type of equation, okay, S is complex variable, so root of this equation has any root in the right half plane. Is his question, because if there is any of roots in the right half plane, that means the system is unstable. It really doesn't matter where there is a feedback or not. Okay, so let me draw this. This is S plane. This sigma j omega. Okay, if there is this type of pole, this is the RHP, right? This RHP. If pole occurs here, they appear as a complex conjugate pair. Okay, and sometimes the real pole appears here, then system becomes unstable. No, it's not unstable. It has right half plane pole. No, zero. Root. Okay, root. Here in the feedback system, we assume this is the loop gain. This is loop gain. And this term, 1 plus TMS equals 0, is called characteristic equation. Characteristic equation. And the root of characteristic equation They are called poles, system poles, natural modes, and eigenvalues. Okay. So you have this. Originally, it was purely mathematical problem, but somehow we are making use of it to analyze our feedback system. Then this becomes a loop gain. 1 plus loop gain equals 0 becomes characteristic equation. And the solution of this equation or root of this equation is called pole or natural mode or eigenvalues. Okay, and this is a characteristic equation. Right. So to evaluate this, the presence of RHP root in this equation, we are just using this one, TMS, polar product of TMS. That is the Nyquist criterion. So the essence of Nyquist criterion is something like this. We assume this, suppose TMS is given by this. We have S in the denominator and S plus omega P1. Okay, this is the pole zero expression. We are not using the frequency response format. In this Nyquist, this is the standard format. So somehow we modified this. Maybe then there is some constant. Assume that constant is 1. Oh, not 1. Okay. Suppose this is characteristic equation, TMS equals 0 is 1. This equals 0 is nothing. Okay. It's meaningless. Okay. You are interested in the root of this equation, not root of this equation equals 0 equation. In other words, this TMS equals 0 is nothing. Okay. There is no meaning. Maybe this is a simple equation, but there is no engineering value. So this equation, they are entirely different. 1 plus something equals 0. And the something is 0 is utterly different. Okay, so you are interested in this, not this one. Okay, for this, maybe there is a RHP pole here. That's okay. That's okay. You are worrying about the RHP root in here, not here. Okay, so TMS can be anything. Okay, but we assume that, and we plot the Bode plot of this one. Right. So I'll upload this lecture slide. So you can take note here now. That's fine. Then there's an integrator. Why we need the integrator? Because DC regulation. For DC regulation, we need this in the loop gain S. Okay. Otherwise, we cannot regulate output at fixed value. So this is necessary. So -1 slope, and we have maybe this one goes up to this, and we have minus another pole. First pole is coming, so -2 is here, and another pole is coming here, then -3. Okay, so this is omega P1, omega P2. Okay. This is a magnitude. And how about phase? Phase starts -90. It ends at -270. Okay? So maybe phase is something like this. Final phase is -270. And somewhere here, you have -180 degree line. Okay, no. Oh boy. Oh, I'm sorry. Let me define this. Okay, I'm in trouble now. This graph looks funny, but suppose this is minus 180. Okay, so they're out of scale. Oh boy. I should be very careful in doing it. Something like this. Okay, this phase is start from 90 degree. Then phase margin. This is 0 dB line. The phase margin is evaluated at this frequency, and difference phase at this 0 dB crossover frequency and minus 180 is phase margin. So it has positive phase margin. So this converter is stable, right? Stable. Okay, this is our previous knowledge, and let's talk about this Nyquist criterion. So, from the Nyquist stability criterion, we want to know how many roots are in the right half plane. Okay, so this contour, there is a contour. So we encircle this and except this one. This is pole at the origin. Then this is the singular point. So we should avoid this, and we take this path. It goes like this and go back like this and go like this, and we avoid this like this. Okay. So this part is 1. This part is 2. This part is 3. And this part is 4. All right. So Nyquist proposed this. Actually, Cauchy proposed this. We walk around this, and this R is infinity. Radius of this semicircle is infinity. That means it encompasses all the RHP of S-plane, and we travel contour of this, contour of this, contour of this, and we map along this S variable through this equation. Okay, that procedure is explained in the control book, and I explained in great detail in the last semester. Okay, so you evaluate this. This is a J omega axis. This axis is what? Real frequency axis. Okay, so you start here and you start walking toward this. That is same as traveling in this direction. In this direction in frequency domain. Okay, and then this is the polar product of this. So polar product of this start at high value, very large value at minus 90 degree. So it start out from here. So it start out from here, somewhere here. Okay, and it goes like this. Okay, so this line segment maps to this one, this circular segment. So this is 1 prime. Okay, and we go around this. As this is radius is infinity, so this is very large. This is very large. Then magnitude of this becomes very small. Okay, so this path 2 is mapped here. This is 2 prime. Okay, so let me repeat. So you start here and going out like this, and then you take a look at this, and you draw polar plot using this. Okay, the polar plot should start somewhere here, and assume it goes like this because there is a positive phase margin. There is some angle. This is stable because it passes this line segment A. We know this is stable, but I'm talking about the Nyquist stability criterion. So along this mapped to here, and this infinity semicircle is mapped at this point. Okay, and you go this direction. This is the minus frequency axis, which is not existing in the real world. Okay, this is not physical quantity. This is mathematical quantity and imaginary quantity, and that is because of symmetry of this complex variable, the result is mirror image of this. Okay, so this one will be something like this, mirror image of this. Okay, and it goes to this like this. This is 3 prime, right? And okay, and you go this. So this radius is very small, s is very small. Then this is in the denominator. This becomes infinity large. Plus infinity and negative infinity, they are merged. Okay, mathematically the same point. So eventually, this will go around, and this will go around. It should come back like this. All right. So if you travel along this Nyquist path, doing some mapping, so you know this part, and this part is collapsed to this one point, and this part is just a mirror image of this, and this part is just the infinity line. So no detailed knowledge is necessary at those two regions. So this one, okay. So now you have this, right? Then Nyquist analysis says this is a critical point, and when you are going to this origin without encircling this, okay, then there is no RHP loop. System is stable, right? System is stable. Okay, let me finish up this. Suppose this gain is increased somehow, gain is raised like this, or this polar plot is expanded out. Then it goes this direction. Then system gotta be unstable. Okay? Then the situation is shown here. So you increased this, somehow this much. Okay? Then at the crossover frequency, the phase is smaller than, more negative than this minus 180 degree. That means it, at this frequency, it passes unicircle somewhere here. Okay? That is unstable, right? Means this polar plot trajectory must pass this line segment C, which is unstable. Okay? If you draw this, if you draw the polar plot of this, then let me use this some other color. I have many colors here. Then it's going like this, and mirror image of this part is going like this, and it's going like this, and they merge together. All right. So first one is this one. Okay, you are encircling this. There is no problem. You don't encircle this my finger, but now you go like this. Then you should break my finger once, twice. Okay, that means there are two RHP roots in this equation. So system is unstable. Okay, 1 or 2, that doesn't matter. If there is a 1 other than any number, then 0, then you are in trouble. Okay, so stability requirement is written here. Nyquist criterion is summarized like this: G equals N plus P. N is right plane root, which should be 0. Okay, otherwise, system is stable. And N is number of encirclement, all right? And P is number of positive pole in TMS. That does not mean system is unstable. We are interested in 1 plus TMS equals to not this one. So it really doesn't matter. Okay, but this number, this is the equationship. This relationship is coming from the Cauchy's theorem and modified by Nyquist. Okay, for the most case, this P is 0. Okay, for most cases, P is 0. Then G is N. That means if this Nyquist plot encircle this point, system is stable. Unstable. Converter is unstable. All right. Then we forget about everything about this Nyquist story. And finally, we just remember this. When this polar plot drawn this using this passes this part, then stable. If it goes this square point, marginally stable. If it goes this line segment to C, is unstable. Okay, that is our previous discussions. That is the simplified discussions about stability. This is the comprehensive. It can explain for the all cases. Okay, this is very comprehensive one. Previous one is the very simplified one, but 99% of your case, you are only using this simplified one, simplified version of Nyquist analysis. Okay, going through all the details of this Nyquist analysis is necessary. Okay, at least once. Then most people or myself, even myself, forget about that. All of them. Okay, when I teach it, I remind it. Okay, but it's very complicated. All right, I'm just remembering this one. Is more than enough, and remembering this one is more than enough. Okay. Next time, I'll discuss the case of conditionally stable system. Okay, conditionally stable system is some special system that can be also explained using this simplified this stability criteria. All right. Oh, 5 minutes. All right. Okay. Thank you. See you next week. Thank you for your attention.